Have you ever wondered what's really going on deep inside your computer? I mean, way down at the fundamental level, right where your code meets the metal. Well, today, that's exactly where we're going. We're taking a journey into the world of assembly language. And to guide us, we're going to use a pretty cool map, the table of contents from a classic assembly textbook. It lays out the entire learning path, from novice all the way to expert.
I mean, seriously, think about it for a second. You write a line of code in Python or Java, you hit run, and somehow, magically, your processor knows exactly what to do. There's this incredible translation that happens, a journey from a high-level idea down to the raw instructions a machine can actually understand. That's the journey we're exploring, by following the exact path laid out for someone learning the language of the machine itself.
And this right here is our map. We're literally going to walk through the structure of this book, almost chapter by chapter, to understand the logical steps you'd take to learn assembly. See, by looking at how it's taught, we're going to get a really clear picture of what it is and why it's still so incredibly powerful.
Our tour today is broken down into 5 key stages. First up, we'll start with the most important question: why? Then we'll get to know the hardware itself. After that, we'll check out the programmer's toolkit before, actually speaking the language. And finally, we'll see how all of this connects to the advanced tech we all use every single day.
So our first stop tackles the big one, the question right from Chapter 1. In a world with all these high-level, easy-to-use languages, why would anyone even bother with assembly today?
Well, the book lays out some really compelling reasons. And listen, it's not about spending your days writing low-level code. It's about gaining this deep, profound understanding of how your computer's architecture actually works. You learn what your compiler is doing behind the scenes, and you get your first real introduction to concepts like interrupts, these tiny signals that are the absolute bedrock of how your computer can multitask.
Okay, so once you understand why you're learning this stuff, the next logical step is to understand who or what you're speaking to. And in this case, that's the machine itself.
Chapters 2 and 3 are all about this. Chapter 2 is kind of like the machine's physical blueprint. It dives into the CPU, its registers, memory, all that stuff. But then Chapter 3 gets into something even more fundamental. How does a machine that only understands on and off represent, well, everything?
And this slide just illustrates the answer brilliantly. We see numbers, we see letters, pictures. The computer? It just sees ones and zeros. Chapter 3 is all about how you translate between these two worlds, how numbers and even text get encoded into binary. Mastering this is really the first big step to learning how to think like the machine. Okay, so you get the machine. Now, what tools do you actually use to build something? I mean, you can't just write code in a text file and expect it to run, right? There's a whole process.
What's so cool here is how it simplifies this whole tool chain idea from Chapter 5. First, your human-readable code gets turned into machine code by the assembler. Then the linker comes in and connects your code with any other bits and pieces it needs. And finally, the loader puts the finished program into memory so the CPU can run it. Assemble, link, load. Simple as that.
And of course, the toolkit isn't just about building, it's also about fixing. Chapter 6 is dedicated entirely to the debugger. Think of it as your magnifying glass. It lets you step through your code one instruction at a time, check out what's in memory, and see exactly what the CPU is doing. It is absolutely indispensable.
All right, our tools are ready. We understand the machine we're talking to. Now it's finally time to actually start communicating with the processor. It's time to learn the words of the language.
This is the heart of it all, really. Chapter 7 lays out the instruction set. You can think of these as the basic verbs of the computer's language. Each one is a simple, direct command to the CPU, like move this piece of data over here or add these two numbers together.
And these commands, they fall into a few key categories. You got instructions for just moving data around, you have your arithmetic instructions for doing math, you got logical operations for comparing things, and, crucially, control instructions that let you create loops and if statements, the stuff that gives your program logic and flow.
But look, a random pile of instructions isn't a program any more than a random pile of words is a novel. You need structure, and that's where chapters 9 and 12 come in. They cover stacks and functions, which are the fundamental ways programmers organize complex code into reusable, manageable blocks. This is how you go from just shouting simple commands to building sophisticated applications.
Okay, this is where it all comes together. This is where a deep understanding of assembly connects directly to the technology we use every single day, from cybersecurity all the way to multi-core processors.
Just take a look at these chapter titles from later in the book.
Chapter 15, Stack Buffer Overflow. Chapter 19, Parallel Processing. I mean, these aren't just academic exercises. They are critical, real-world concepts that are hugely important today.
So the crucial point here is the real-world connection. Learning about Stack Overflows and assembly is the first step to understanding exactly how hackers can trick a program. Learning about parallel processing, that's just learning how your dual-core or quad-core processor actually splits up work. And understanding interrupts, from Chapter 20, that's the key to how your computer can do a million things at once without crashing.
So, as you can see, this book's structure shows that learning assembly is a complete journey. It starts with that simple question of why, builds a solid foundation of how the machine thinks, gives you the tools, teaches you the language, and then connects it all to the most advanced topics in computing today.
So, there you have it. You've just taken a guided tour of the language that sits closest to the hardware. You've seen the blueprint for how software truly talks to the machine. The only question left is, with that knowledge, what would you build?